Just kind of line this up. There we go. All right, cool. So this is the second half of chapter 6, so we're doing it a little bit out of order. But like I said, the test will be over both chapter 5 and chapter 6, right? And we, in essence, got through, so just to kind of a quick refresher, we went through the Internet Protocol Suite last time and started on the first layer of that when we discussed this section here. Who can give me a different name for the Internet Protocol Suite? We're just going to go ahead and write Aiden's name on the board.
Yeah,
okay?
I think
Just get that out of the way.
way.
But he showed us his cool Python code, so it's
It would say IPS.
huh?
IPS, Internet Protocol Standard.
Internet Protocol Suite.
Oh.
But then we've learned a different name for that. Does anybody remember another name? It's also referred to as the TCP/IP model, right? Or the DoD model. That was another name that we said that you could use. Why the DoD model? Department of Defense.
I did not actually read that yet.
So this was actually invented as part of a Department of Defense project. What was the division of the Department of Defense that actually came up with this?
Isn't it ARPA?
ARPA, which later was changed.
DARPA.
Yeah, when TCP/IP, when that was officially kind of released, it was under DARPA, and
Yeah,
it changed
that
the
was
name.
underneath the defense.
For defense, that's right, exactly right. Just trying to refresh our memory on that stuff. What time frame are we talking about?
This is
Late 69.
1969 was when the ARPA version kind of started, and then early 70s was when DARPA began to release the stuff that that was connected with those two guys that we said were sort of credited with being the fathers of the architect of the internet. Does anybody remember their names? Bob.
And Larry?
Bob.
It was like Bob Ian.
Bob and Vince. So Bob Kahn and Vince Cerf were the two guys. And I wanted to remind you of that because we're going to watch a video in just a few minutes here where Vince Cerf actually does some talking in the video.
Is that why it's called surfing the web?
That would be pretty funny if it was. I mean, that alone is worthy of Levi. But if it was called surfing the web like that, we would have to spell it this way. Right? So that would be, not that way, I'm sorry. This isn't a PH, this is an F. So we would have to write it like that. Right? Because that's how you spell his last name. I like that. Somebody should use that. Okay, so we talked about the breaking down of the URL. Subdomain, what the SLD and the TLD portion was of the domain name, just trying to refresh your memory about the type of stuff that we were talking about, and you can go back and review this in the textbook. And then, but we said the Internet Protocol Suite is made up of 4 abstract layers, and we talked about the first layer, which was the application layer. Can anybody, and so we said in the application layer, we have all these services that are available, and each service has its own protocol. Can anybody give me a protocol that we talked about? Levi, is that your pencil on the floor? Mm-hmm. Okay, so I want to make sure you didn't lose your pencil. If you're okay with it being there, I'm okay with it being there. That's really bugging me. We pick it up. I'm just kidding. Nobody remembers the protocol? Aiden? SMTP, right? SMTP stands for what?
Simple mail transfer protocol.
Simple mail transfer protocol. So we actually discussed, I think, 3 different mail protocols. Another one was POP, P-O-P, Post Office Protocol. IMAP was the other one. Internet Mail Application Protocol, maybe? What is it? Internet Message Access Protocol was nowhere near what it was. But that's okay. I'm not going to quiz you guys on what the meanings are. We talked about FTP, which was FTP and SFTP, which was used for, anybody remember? Transferring files, right? File transfer protocol is what that stands for. And then the the World Wide Web, which we said was actually a service, right? Not really, not equivalent to the internet. They're not the same thing. The web is just a service that runs on the internet. And so when we're requesting web pages on the web, what's the protocol used for that? Yes? HTTP or HTTPS, right? So hypertext transfer protocol or hypertext transfer protocol secure, which is what we see more commonly now. So that it's actually, what does the S mean? Since we've learned about the stuff that we learned about in the last chapter, what's actually happening when we slap that S on the end? What is that telling us is going on?
Secure.
It's secure, so what's actually, what did we just discuss, and what did we just take a quiz on that's actually happening? Why is it secure? Huh?
Encrypting it.
It's encrypting it, right? So, so when you add the S on there, it's actually, your data is not flying across the web, or information that you're entering in on a web page is not going across unencrypted, where someone could intercept that signal and read what's there. It's been encrypted and then it's decrypted on the other end, right? All right, cool. So that was just a quick refresher about the stuff that we talked about in the first part of the chapter. We're going to move on to the next. So the first layer was called what?
Application.
The application layer. Now we're going to move on to the next layer, which was the transport layer. All right, and so there's my marker. I knew I had a better one. For the transport layer, one of the things we talked about last time were IP addresses, and so once the server's IP address has been identified, what is it most likely initially? It's not an IP, but we use a
URL.
huh?
URL.
Well, a URL, maybe if we're accessing a website, but so instead of an IP address for the server that we're requesting those web pages from, we use a, what is this? Huh? Domain name, right? So we use a domain name, and then we use the DNS, the domain name system. We use servers that are part of DNS to look up that name and convert it to the associated IP address. Who was it that said domain? Okay. And so once we know what IP address we're targeting, which is, you can think of as sort of like the address for your house, right? Each server has its own, across the internet, has its own unique IP address. Then this layer is responsible for preparing the data for transmission, okay? And using different transport layer protocols. And so the biggies that we're going to discuss are TCP and UDP. And what I want to highlight between the two, this stands for transmission control protocol. And this stands for user datagram protocol. And I just want to kind of highlight some key differences between the two. Both are, what they do is they take the data and they break it down into smaller pieces. So both do this, but they call these things, one calls it, TCP calls them packets, whereas UDP
Is that an error in the first thing
hang on just one second.
when you're done?
What are we saying? Pieces. Were you talking about an arrow or an arrow?
Read the first.
Break down. I mean, they really break it down. Okay. I mean, there's one thing when you break something down, but when you break it down, I mean, you just ask G, all right? I know what's going on. It's this doubly. It's like in 2 times the valor. If you guys know that movie, break down data into. I'll write your name on the board if anybody can give me the name of that. If your name's already on the board. If your name's not already on the board,
Do I get it twice?
no, you don't get it twice.
Give it to me for him.
Break down data.
Yeah,
You can assign it to someone else. You're gonna
I
give it.
know.
Okay.
This.
What?
This.
Break down data into smaller pieces called packets. That's what that was supposed to say. All right, there we go. Whereas UDP refers to those as datagrams. All right. So that's one difference. Packets. Another difference is that TCP numbers the packets. So packets are numbered. So can be reassembled when reach server. So that way we know we're putting the packets back together in the correct order. All right. Doesn't number datagrams. So if the packets are numbered on the TCP side, not only can we put the packets in order, but what else does that make us aware of? If I'm sending you 15 packets of data, all numbered 1 through 15, and you get 1, 2, 3, 4, 5, 7, and all the way to 15 after that, what does that tell you? You know that you're missing a packet, right? So because these are numbered, you can find out whether or not all of them showed up on the other end. But because the datagrams are not numbered, there's no way to verify. So no way to verify all successfully made it to destination. So because of that, which one do you think is more reliable, TCP or UDP? TCP is, right? Because we can actually determine if a packet is missing. If packet is missing, can be requested again. So we're counting up the packets. We see we're missing number 6. Send me number 6. And then we send that request to the client. The client says, oh, here it is. Passes off that packet. And so we can verify that all of the packets got there. So it's a lot more reliable. So this is considered what happens when I look away. Considered is considered reliable. Because either every packet will arrive, or we'll know if one doesn't, or a failure will be known. All right. So if that's the case, if TCP is more reliable, we know that the packet made it there, we can request it. If it didn't, then why even have UDP? Why is UDP even still around? Anybody know or want to take a guess? Amy?
TCP takes more time if it needs to re-request it. So, in like videos and things, you can't go back a few seconds and request the packet again.
Right. Yeah, exactly. He's exactly right. So this is more reliable, but it's slower because, or potentially slower, because if everything doesn't go through, then I'm gonna request it again, and so there's just kind of back and forth until you get everything there. UDP is used when speed is really the issue, right? So I'm just sending this information out, and if you lose a little bit of it, oh well. My job is to get it to you as fast as I can. And so this is important for playing like video games, right? Where you've got a bunch of people that are connected together, and the game can't stop and wait for something to come through, right? It needs to happen as soon as possible. Or like live streaming video or live streaming audio, it's live, right? So we can't have the delays of kind of the conversation back and forth. So UDP is the faster one for that reason. Used when speed is the priority. So, playing video games.
So
Real time. Huh?
So when your parents tell you to pause your game, you really can't.
Real time. I'm not even going to answer that question. I'll just give my son ammunition.
I don't even like play video. It's like
But if we install Flight Simulator back on the machine, then we're going to have that problem. So it'll come up, right?
do you have the new one?
So playing videos. I mean, we've all been there, right? There's nothing worse than you're in the middle of solitaire and you're right there on the end where you're expecting those cards to jump across the screen, you know, and you find out you've got a TCP connection, so you're having to wait for that to happen. Nobody likes that experience, you know. So, all right. So, because of this, because of the way information is handled, the internet is considered to be fault tolerant, and we've talked about this before. But what's the basic idea behind a system being fault tolerant? Does anybody besides Aiden remember?
If one thing fails, the whole thing doesn't fail.
Yeah, right. If it's fault tolerant, then there could be an error or an issue without the whole system crashing, right? And so obviously that would be important for the internet, because just because my solitaire game got messed up doesn't mean that, you know, your entire company's network should go down. So it's fault tolerant. An error can occur. An error can occur, and system will not fail. All right. Questions about the transport layer? Anybody? Move over here. All right, let's talk about the internet layer. The internet layer, where am I? Okay, there we go. Put that over here. All right. The internet layer. So the internet layer is responsible for attaching each packet to the appropriate IP address, creating a way to track packets as they travel the physical internet. So we've figured out where we're sending it. We've got the IP address, right? We've broken these packets down depending on the protocol that we're using, TCP, UDP. We've numbered them or not, but we've got the packets ready for distribution. So the internet layer is responsible for tracking these packets as they go across the physical internet. Provides a way to track packets as travel the physical internet. Most traffic is routed using IPv4. Which is 32-bit. So that means 2 to the 32 possibilities. I think we talked about this last time, where we showed you an example of an IP4 address for a machine. Did we talk about that? Does that sound familiar?
Yeah.
IP4 versus IP6.
Yes.
And so an example we said of this might be something like, 157.166.7.201, something like that, where you basically have 4 groups of up to 3 numbers, right? And numbers 0 through 9. So like the numbers using the decimal system, just 0 through 9. And so that's just an example of that. You guys have probably seen that before. And when this was created in the early 1980s, we were like, we're good, we won't ever need more than this, right? They picked a really big number, 32-bit, 2 to the 32 possibilities, we'll be fine. Now here we are in 2021, right? And they weren't even thinking back then of all the connected devices. Yes?
2022.
That's right, 2022, see? I mean, 2 to the 32 wouldn't even get me into 2022. I had to chop it off at 2021. Thank you, appreciate that. You on the board yet, Isaiah? You get to get put on the board, but you have to sit in the desk of shame. I'm sorry, you corrected the teacher. All right, so 2022, not only do we have computers now that are connected to networks, but we've got all these cell phones, cellular devices, and not only cell phones, but I mean, you've got watches, smart watches, all these different smart devices that have unique IP addresses and all this kind of stuff. So it's way more than what is it? What's so funny?
Can you say watches again?
Watches! So I'm just trying to keep you guys awake, If it makes you laugh, then my mission has been accomplished. And so they actually realized relatively early on that, okay, we were not on par at all with what we thought we needed. And so the late 90s, IP version 6 was introduced. And late 90s,
Was there ever a version 5?
what's that?
Was there ever a version 5?
Yes. Yeah, so version 5 just wasn't popular enough to stick around. So IP version 6 seems to have stuck, and this is uses in late time IP is introduced using 128-bit system, so 2 to the 128 possibilities. And so basically, this is like more than the number of stars in the known universe. This is a huge number that what we say today is this will be plenty, we'll never run out. We'll see, but that's the plan. And so these addresses are written in uses hexadecimal. And so an example of this, did I write down an actual example? I'm not going to write it down, but basically four characters per section. Eight sections separated by a colon. And I'll pull it up on my computer in just a minute so we can see an example of that. There's one in the book, if you want to look it up. But it's definitely way more complicated than this. And so this hopefully will support all of the devices going forward. So the goal is then for all these IP4 addresses to get moved to IPv6, right? So all of the, most systems that are still using IPv4, they've already got IPv6 versions that are associated with their machines as well, so that whenever IP version 4 is finally fully deprecated, do you guys know what that word means, deprecated? It's just when we're in the programming world, we see that all the time because there may be some particular method or function that you've been used to using in the language, and they say, you know what, that function's going away. So it's been deprecated, which means that it's been flagged for retirement. So one day you're going to go to use the language, and that function's not going to be there. So quit using it, right? Go ahead and move on to something else. So this has been, IPv4 is in essence been deprecated. It's going away, and so we're moving to IPv6. That's the plan. So hopefully that'll be a seamless experience. Most of us will just never know that happens. There is one other important address. Is the MAC address, M-A, all capitals, M-A-C address. And that has nothing to do with Apple devices.
Good.
Yes. One other important address is the MAC address, a unique hexadecimal ID assigned by a device's manufacturer. So your machine, if you buy a machine or a cell phone, any kind of device that's going to be able to connect to a network, it's got a hard-coded MAC address for that machine. That's not going to change, right? That's what the manufacturer has assigned to it. So in theory, if you know the MAC address, you should be able to figure out who manufactured it and what type of device it is, because that's all been identified by the manufacturer. But the reality is that MAC addresses are very easy to spoof, so just because you supposedly know the MAC address of what's connecting to your network, you may not necessarily know what type of device that is. So let's look, I'm going to run a command on here just to see what's on this machine. And if you have a Windows machine, you can Scotland. And that's what that was. I can't do a Scottish accent very well. We're Vikings, it's an occupational hazard.
I don't think you realized that we couldn't see the picture.
Oh, you couldn't? Okay. That was my, oh yeah, I'm sharing it like that. That was my one, I have to say that when I try to do a Scottish accent. Let's see. Alright, let's go. You can launch a command prompt. So if you don't know how to launch a command prompt on Windows, you just type in CMD down where your little Windows, can I do that from here? Let's see, where is it? There you are. So like if you click down here and you just type in CMD like that, it'll find it. It'll find that app, the command prompt app, and you can launch that.
You can also do Windows R.
You can do Windows R, which means run, right? So Windows R, there's all kinds of ways, little hotkeys you could use to launch that. So if I type in IP config /all, so there's a whole lot going on right now. So let's see, this is going to be fun for the people that are watching this on video. I'm going to take this loose here. I'm going to try to come over here to the actual TV, and let's see if I can, yeah, this isn't going to be the best experience. But anyway, so can you guys read that from the back? Can you guys see what all those say? So you see how we've got IPv6 right here? So there's our IPv6 address, right? All of those numbers there separated by colons. Like I said, that's a hexadecimal value. So I bet my voice is really loud right now on the phone. I just thought about that. It's probably not good. Sorry if I just busted your speakers. Yeah, someone wearing headphones. They just woke up. And notice this says this is preferred, right? So this IPv6 is preferred. Here's the old IPv4 address, right? And then the other thing that's important that we were just talking about was the MAC address, which on here it's listed as the physical address, all right? So that's what the MAC address looks like. Again, a hexadecimal value, 2 characters per section, divided by separated by dashes. So that's what the MAC address looks like. So you've got one of those on your phone. You've got one of those on all of your computers. Like I said, any device that's going to connect to a network is going to have a MAC address associated with it. And when you're looking at if you ever look at traffic that's coming through your router maybe at home, you can see which devices are connecting based on their MAC addresses. All right. Any questions about the internet layer and specifically questions related to these important addresses? So the IP address it lets the world outside of us know our location, right? As far as the internet, if somebody wants to send something to my machine across the internet, just like I'm going to mail a package to someone, I got to know what their street address is, right? In town and all that sort of stuff. That's what the IP address does for you on the internet, right? And then the MAC address identifies your specific machine. It's supposed to represent your manufacturer. You can probably find out model and all kinds of stuff if you know the MAC address, if you really have the true MAC address for a device. Okay, last layer is the link layer. So we've got the application layer, the transport layer, the internet layer, and then the link layer. And the link layer, we're not going to say much about that at all. The details behind that are kind of outside the scope of this class. I had a marker somewhere. You guys see it?
I think it grew some legs.
Oh, here it is. What's that?
I said I think it grew some legs and ran away.
Oh, ran away. Okay. Well, didn't run that far. I got it. Tried to get away, but all right. The link layer is the lowest layer. Lowest layer of the Internet Protocol Suite. Lowest level. That's what I'm going to say. I'm sorry. Lowest level of IP suite layers. Say it that way. And it manages interface between physically connected nodes on local networks. Includes protocols, like ARP, Address Resolution Protocol, bless you, and RARP. That sounds like one of my sneezes.
No, yours are still louder.
No, there's someone at my church that literally sounds like an earthquake. It's scary. Someone at my church, like, you don't want to be there.
You don't want to be there.
There's nothing.
So
It's so mid.
this protocol, and the last one they mentioned in the book is NDP, which is Neighbor Discovery protocol. And so like I said, we're not gonna, just to kind of give you this high level overview of what this layer includes. It's beyond the scope of this course, which is good because this is not anything that I've ever really had much exposure to. I don't know much about
Are
it.
you saying we're not smart enough to understand it?
Yeah.
That's, I'm saying I'm not smart enough to teach it to you, right?
Aiden, do you want to teach it?
I've never heard of it.
No, I just don't know much about it. I mean, like ARP, those aren't familiar to me at all. So that's kind of, with some of this stuff, and I think I've talked to you guys about this before, you tend to sort of be either a software guy or a hardware guy, right? In the computer science world, if you're going to be the technical person that kind of gets down in the weeds of it. And so the software guy's writing code like Abe did, right? And you know enough to sort of, and don't get me wrong, there are some software guys that are excellent on the hardware guy. I'm just not like that guy. I kind of focus more on the software side. And so when it came to linking devices together, I know just enough to be dangerous, right? A lot of Googling to try to make it work. There were guys that were way smarter than me on the network side of things that they maybe couldn't, program at all, but they were very skilled on that side. So it's just too much information for somebody to know it all. And you tend to specialize in a particular area and kind of stay in that niche. All right, let's talk about how we doing on time? Wow, are we almost out of time?
Yeah.
10 minutes from time? Wow, I really wanted to watch this video. All right, I'm going to show you this video here, all right? Because I think this will be more fun than me lecturing on this last portion, but you guys are going to have to read the last portion of it for your homework. So the last portion has to do with the physical internet. That's not actually, the physical internet is not really a named layer in the internet protocol suite, but that exists, right? There are wires and devices that are actually connecting all this stuff up together, as well as waves that are being transmitted wirelessly and all that kind of stuff. So the physical internet includes things like your modem that you have in your home, right? Or routers that you have in your home, and also routers that are around the world. And then also what's used to actually transmit the signals, like either electricity, light, or radio waves, right? So the book's going to talk about that some more, but I wanted to show you guys this video that was just basically kind of an overview of the way that routers are used to send information to the appropriate place. And this, like I said, this is the video that had this surf in it, which I thought was interesting. And I hope I watched this on my YouTube channel. Let's see. I may have to just type it in. Creating network. The internet. That's it. That's the. Yes, here we go.
I am a software engineer here at Spotify.
That's all right. Gonna have to. Go. Turn that down. All right. Yeah, go for it. I'm gonna try this one more time. Let's see if this. There we go. Cool. All right, can everybody see that?
Yep.
Yeah, cool. So we'll back it up a little bit so you guys can meet Len Root.
7, 6, 5, 4, 3, 2, 1.
Hi, my name is Lynn Root. I am a software engineer here at Spotify, and I'll be the first to admit that I often take for granted the reliability of the internet. The sheer amount of information zooming around the internet is astonishing. How is it possible for every piece of data to be delivered to you reliably? Say you want to play a song from Spotify. It seems like your computer connects directly to Spotify's servers, and Spotify sends you a song on a direct, dedicated line. But actually, that's not how the internet works. If the internet were made of direct dedicated connections, it would be impossible to keep things working as millions of users join, especially since there's no guarantee that every wire and computer is working all the time. Instead, data travels on the internet in a much less direct fashion.
Many, many years ago, in the early 1970s, my partner Bob Kahn and I began working on the design of what we now call the internet. Bob and I had the responsibility and the opportunity to design the internet's protocols and its architecture. So we persisted in participating in the internet's growth and evolution for all of this time up to and including the present. The way information gets transferred from one computer to another is pretty interesting. It need not follow a fixed path. In fact, your path may change in the midst of a computer-to-computer conversation. Information on the internet goes from one computer to another in what we call a packet of information. And a packet travels from one place to another on the internet a lot like how you might get from one place to another in a car. Depending on traffic congestion or road conditions, you might choose or be forced to take a different route to get to the same place each time you travel. And just as you can transport all sorts of stuff inside a car, many kinds of digital information can be sent with IP packets, but there are some limits. What if, for example, you need to move a space shuttle from where it was built to where it will be launched? The shuttle won't fit in one truck, so it needs to be broken down into pieces, transported using a fleet of trucks. They could all take different routes and might get to the destination at different times, but once all the pieces are there, you can reassemble the pieces into the complete shuttle and it'll be ready for launch. On the internet, the details work similarly. If you have a very large image that you want to send to a friend or upload to a website, that image might be made up of tens of millions of bits or ones and zeros, too many to send along in one packet. Since it's data on a computer, the computer sending the image can quickly break it into hundreds or even thousands of smaller parts called packets. Unlike cars or trucks, these packets don't have drivers and they don't choose their route. Each packet has the internet address of where it came from and where it's going. Special computers on the internet called routers act like traffic managers to keep the packets moving through the networks smoothly. If one route is congested, individual packets may travel different routes through the internet, and they may arrive at the destination at slightly different times or even out of order.
So let's talk about how this works. As part of the internet protocol, every router keeps track of multiple paths for sending packets, and it chooses the cheapest available path for each piece of data based on destination IP address for the packet. Cheapest in this case doesn't mean cost, but time and non-technical factors such as politics and relationships between companies. Often the best route for data to travel isn't necessarily the most direct. Having options for paths makes the network fault tolerant, which means the network can keep sending packets even if something goes horribly wrong. This is the basis for a key principle of the internet, reliability. Now, what if you want to request some data and not everything is delivered? Say you want to listen to a song. How can you be 100% sure all the data will be delivered so the song plays perfectly? Introducing your new best friend TCP, Transmission Control Protocol. TCP manages the sending and receiving of all your data as packets. Think of it like a guaranteed mail service. When you request a song on your device, Spotify sends a song broken up into many packets. When your packets arrive, TCP does a full inventory and sends back acknowledgments of each packet received. If all packets are there, TCP signs for your delivery and you're done. If TCP finds some packets are missing, it won't sign. Otherwise, your song wouldn't sound as good, or portions of the song could be missing. For each missing or incomplete packet, Spotify will resend them. Once TCP verifies the delivery of many packets for that one song request, your song will start to play. What's great about the TCP and router systems is they're scalable. They can work with 8 devices or 8 billion devices. In fact, because of these principles of fault tolerance and redundancy, the more routers we add, the more reliable the internet becomes. What's also great is we can grow and scale the internet without interrupting service for anybody using it.
The internet is made of hundreds of thousands of networks and billions of computers and devices connected physically. These different systems that make up the internet connect to each other, communicate with each other, and work together because of agreed upon standards for how data is sent around on the internet. Computing devices, or routers along the internet, help all the packets make their way to the destination where they're reassembled if necessary in order. This happens billions of times a day, whether you and others are sending an email, visiting a web page, doing a video chat, using a mobile app, or when sensors or devices on the internet talk to each other.
So that was it. Any questions? Oh, yeah. So that was Vince Cerf, the older gentleman was, who was one of the founders of all this. Yes, I know. All right, so we're basically out of time, so you guys will just have to look online. I'll be honest, I haven't figured out what I want you to do for your homework assignment this time. Does anybody have any suggestions?
Just the reading?
Just the reading.
That's the reading. Just the reading. Yeah, that's a little
You wrote a
light.
poem.
That's a little light. It's just a tough one to give you an assignment on.
We wrote a poem about it.
A poem, yeah. I think we might do some research on one of the topics. I just think that might be helpful.
Wait, how do you say it?
Huh?
How do you say poem?
What's that?
How do you say it?
Poem? All right, get out of here. All right. I'll see you guys later.